All right, there, we're now recording. I don't know how to turn that monitor on.
That was a not.
Odd strategy is the easiest one. Doing a bit of the old UDU. What's the even strategy?
Cosine squared, and then you can use the power reduction formula.
Power reduction formula for cosine squared is 1 plus the sine of 2x over 2. We're going to use that one here. The other one is sine squared is minus sine of 2x
Is it sine or cosine?
with cosine. As soon as I started writing it, I knew that.
I gotta reach all the way back up there.
I know. I'm gonna pull like a lat or something.
Check if you're using just power for that.
There we go. We use the power reduction formulas. Even strategy, have to use the power reduction formula. Let's see if you can get this all the way through. Well, any constants, et cetera, et cetera. Here, 23. They're both done? All right. Okay, so I'm going to go ahead and do this first one. I'm going to pull out one of the cosines. That'll leave me a cosine squared x to replace in the next step. So I'm setting that up as the du. What do I replace the cosine squared with?
Minus sine.
Minus sine squared. You can multiply it out now and then substitute, or you can go ahead and substitute right now. I'm going to go ahead and substitute. U is equal to the sine of x. The du is cosine of x dx. That takes care of that n term over there. And then I'm integrating u squared times 1 minus u squared times du. So eventually I have to multiply it out. I'll do that right now. That's a u squared minus u to the 4th that I'm going to integrate. I'm going to get u cubed over 3 minus u to the 5th over 5 plus c. And I'm going to go ahead and make a jump to replace each u with the sine of x. So the sine of x will be cubed over 3, and then minus my u term, which is the sine of x, 1 power more is to the 5th, over 5, plus c. Is that what you got?
It is, because I forgot how to integrate, and I had sine squared over 2.
I did the same thing with sine.
You forgot the polynomial part?
Yeah, I forgot.
Back to Cal 1. Where?
Wait.
When? How?
Oh,
Why?
isn't there a negative for the cosine x?
It's
Just
no.
The derivative goes positive.
Just no.
Oh,
yeah,
that's
that's
the
negative.
Yeah, okay.
There's the other one. No.
I said don't blow any constants. What did you do?
Blue constant.
Okay, so the next one, we're going to think of cosine to the 4th as cosine squared squared. And then for the cosine squared, we're going to put in 1 plus cosine 2x over 2.
Wow, I blew a constant.
Should I make the noise?
Yes.
That's going inside the parentheses, 1 plus the cosine of 2x over 2. Then I've got to square it. We're going to do the squaring in the next step. Let's go ahead and get that 2 out of the way that's on the bottom. Make sure you square it and pull out a 1/4. Now we'll square it. Get the first term squared. 2 times this product, so I'll get 2 times the cosine of 2x. Plus the last term squared, so I'm going to get a cosine squared of 2x. Now I'm going to make sure I don't lose a constant, so I'm going to go ahead and do a Udu substitution. I'm going to take u to be the 2x, and du is going to give me a 2 times dx. So I'm going to put a 1/2 factor out front and write that as a u integral. So this 1/2 is going to join a 1/4 to give me 1/8. And I'll have 1 plus 2 times the cosine of u plus the cosine squared of u du. And then we know how to integrate all 3 of those. So down here at the bottom of the board, I've got 1/8. I'm integrating in terms of u, so this becomes u. Integral of cosine is a minus sign, so I get minus 2 sine of u. And then remember the integral of cosine squared was u divided by 2 plus the sine of 2u divided by 4. And our last step is to put the 2x back in there. Yes, sir.
Should there be a negative after 2 sine u?
Because you're integrating cosine, not deriving.
Yeah,
I'm integrating the cosine right here.
Yeah,
positive.
so it should stay positive, right?
Yeah.
Oh,
Yeah, okay. I was
I
thinking
blew a-
that, but then I was like, oh, shit.
little constant. Thank you. I only do that just to see if you're paying attention. I slip these mistakes in there on purpose, of course.
I do that on my exam.
I do
Yeah.
that.
See if you're paying attention to screening.
I do that on my web work.
Well, it doesn't help on web work, only on.
I know.
Now each u is equal to 2x. So I'm going to put that in there. Let me erase this one so you can see the answer.
I make mistakes so I can see if I'm paying attention.
And so I get 1/8 of 2x plus 2 times the sine of 2x plus 2x over 2 plus the sine of 4x over 4. And then plus c. And if you want to go further, you can make that a 3x right there. That's cosines and sines are very cut and dry. Both powers are even, do the power reduction formula. If any one of the powers is odd, pull out an odd factor and write a UDU integral right away. Now, this was a web work problem and I saw it done so many different ways. And I want to show you the way that I thought of it. I thought of it as this integral. Recognize that formula there?
Yep.
What is that formula? That's an arc secant. That's the arc secant of u divided by a, but a is just 1. So I'm going to do that, but what we need is the term being squared here, which is a 4x, would match the term outside. So I need this to look just like that. So we do our multiplying by 1. We put a 4 down there where we need it. But I'm putting a 4 on the bottom, so I take it out by putting a 4 on top. Now I'm gonna do the Udu substitution, where u is equal to 4x. So du is 4 times dx. Well, there's the 4 times the dx. So that's gonna come out again. Yes, sir.
Does X not have to be in absolute value?
Now we blow off details like that in calculus too. Right? We're just assuming that that's all positive. I know the general formula has that, but that's a Cal 1 worry. We're in Cal 2 now, we just blow it off.
I love how the more advanced you get, the more mistakes you can make.
Yeah, you just blow it off. So 4 times 1 times dx is du. Then I have my u where I need it, and my u squared where I need it, and we're done. That's the arc secant of u plus c. So it's the arc secant of 4x. And so you did a real clever substitution, so I want to see if I'm able to write this in terms of an arctangent. So let me show you another way to do it. But I always get this one wrong. So here's another way. It's a double substitution, but it's a crazy, clever double substitution. Let's see what happens if we take u to be the entire radical sign. 16x squared minus 1. What's the derivative of that?
It should be 16x over that.
Okay. So derivative of a square root puts 2 times those square roots down here. And then the derivative inside will give us a 32x dx. And so the 2 and the 32 reduce to 16. And so you get du is 16x times the square root of 16x squared minus 1 dx. So dx itself is going to look like, I'm solving for dx, the square root of 16x squared minus 1 times du over 16x is our dx. Now what? Now let's put that in and see what happens. You with me to that point?
Sure. I originally tried this way and then I couldn't figure out how to
I know.
get there.
I get. Okay, so let me substitute it in. So this part here is my u. dx is going to come out for that stuff, and I'm going to leave this back in there. It's going to cancel. Maybe,
No,
figure it out. Let's see what happens to that x. So I'm going to have the 1, the dx becomes the square root of 16x squared minus 1 over 16x du. And there's an x, and that one's a u. Or I could just leave it with the square root of 16x squared minus 1, I don't care. But this part is u, so it will cancel, right? So that's a u, and that's a u.
That is really
And that
clever.
leaves us with 1 over 16x squared du. Well, I got my variables all mixed together, so I can't integrate that with respect to u. So I'm going to go back here and solve this for 16x squared. So I square both sides. U squared is 16x squared minus 1. So u squared plus 1 is the 16x squared. Now I have the arctangent integral.
What kind of maniac solves it this way?
So when he used
And those of you that did solve this way and left out all of this, and you just went from here to here, I thought, ah! How do you do that? That was like child abuse, reverse.
Elder abuse.
that's just
Elder abuse. Okay, you had to slip that one in there.
Well, anybody that's older than you is an elder technically.
So elder is elder. Elder is, you open the door because I can't.
least you get the discounts from the movie theater.
Come on, let's go to Denny's.
At 3 a.m.
Free pancakes. right?
I'm sure you still get carded when you buy alcohol.
Always, so I never buy alcohol. I don't mind you doing this way, but please put the steps in so I don't get lost. Okay,
That's very
that's a
interesting.
lot of stuff. This one is pretty much recognizes. And then today I'm gonna give you so many more tools. You're gonna try to do easy integrals using the more tools. So then you're gonna be really dangerous. Any questions? Okay, so show me steps when you turn in your written work. That's what I'm most interested in, the steps and not the answer. Okay?
Does that for you?
Okay, we're now talking about secants and tangents. And secants and tangents integrated together aren't as easy as sines and cosines. So let's think of all possible ways secants and tangents are related. So we're looking at integrals of the form secant to a power, I think I used an m, times a tangent to a power. Let's write everything we know about secants and tangents. So suppose we tried to make one of them u, what would the du be? So what if u is a tangent? Then what's du gonna be? Secant squared. What if u is equal to a secant? What's du gonna be? Secant of x, tangent of x. Then we had the Pythagorean identity, sine squared plus cosine squared is 1. So if we have sine squared plus cosine squared is 1, and I want to relate secants and tangents, I know tangent is sine over cosine. So if I divide everything by cosine squared, I get that tangent squared plus 1 is secant squared. Or on the other hand, I could say that secant squared minus 1 is tangent squared. So let's see. If I want u to be tangent of x, then I've got to have at least 2 secants in there. And I've got to have another 2 more so that I could write the remaining integral strictly in terms of tangent. So in order for this substitution to work, I've got to have this power as either a 2, 4, 6, m has to be even. N can be anything, but m has to be even for this substitution to work. Do you see why? So that I can write the rest of the integral in terms of this trig function,
Okay, yeah, you can never.
right? M has to be even. I would pull out one of the tangents, then I have to write the remaining integral in terms of tangents. So I'm going to need a secant squared to substitute, a secant squared for the du term. So we're going to use this only in the case when the power on tangent is even. So let's do one of those right quick. And then I'll come back to the other case. Not power on tangent, power on secant. Let me write tangent. Power on secant is even, so that I can have a secant squared in there, and I can have a secant squared substitute out for a tangent. So for example, suppose we're integrating secant to the 6th, tangent, pick your favorite number, 7.
7.
I figured that. Power on tangent is irrelevant. The power on secant is what we're looking for here. I'm actually going to be able to work this integral using both strategies, so that's a good example. So I take one of the tangents out, doesn't matter whether this is even power odd, take one of the tangents out. Oh, I didn't want to take one of the tangents out, right? I want to take a secant squared out. Come back. Come back. I want to take a secant squared out. Let's put that, make that down one. The secant squared out. We always set up the du. So that means tangent has to be u. And that means this has to be written in terms of tangents. So we need to write the rest of the integral. The rest of the integral. In terms of tangent. That's where I needed the even power on the secant after I pulled out a secant squared. So that I can think of secant to the fourth as secant squared squared. And replace each secant squared with tangent squared plus 1. So I'm going to have that as tangent squared x plus 1 squared. Then I've got a tangent to the 7th. And then I've got my secant squared x dx. That's what I was working towards. So now that I can replace tangent with u, secant squared x dx is du. And we're left to integrate u squared plus 1 squared times u to the 7th times du. What do you want to do with that mess that I got left with in terms of u?
Multiply out the u squared plus 1 and then.
Got to multiply it all the way out. So let's replace u squared plus 1 squared with u to the 4th plus 2u squared plus 1. And then we'll send the u to the 7th in. U to the 4th plus 2u squared plus 1. Next step through, we multiply through by u to the 7th. Once we multiply by u to the 7th, we can integrate term by term. So we're going to integrate, let's see, I got to add exponents there. So I'm going to integrate u to the 11th plus 2u to the 9th
Plus u to the 7th.
plus u to the 7th. So we end up with u to the 12 over 12 plus 2u to the 10 over 10 plus u to the 8 over 8 plus c. Last step, replace each u with tangent of x. And tangent to the 12th of x over 12, I'll go ahead and reduce here, plus tangent to the 10th x over 5 plus tangent to the 8th x over 8 plus that constant. It's okay? This way might be shorter for this problem. The other option is to pull out a secant tangent for the du term. That means the rest of the integral has to be written in terms of secant. So in order to get the rest of the terms in terms of secant, what power has to be on the tangent? Has to be odd powered. Has to be an odd power. If the power on tangent is odd, then I can pull out a secant tangent. That leaves me an even power of tangent to be substituted out with this. So if the power on tangent is odd, this one will work. So we had that case with this example, excuse me, so let's do it another way. Let's do it with the secant tangent as the du. Let's see, I'm going to put up a secant of x, tangent of x, dx. So that leaves me a secant to the fifth. I pulled one of these out, so it leaves me a tangent to the sixth. So if my du is secant tangent, then my u is going to be secant, so we get the rest of the integral in terms of secant. So we're going to write all of this in terms of secant of x. So that's why we needed the even power, because this substitutes out even powers of tangent. Tangent squared is secant squared minus 1. So think of the tangent to the 6 as tangent squared cubed. Now I'm going to put my Pythagorean identity in there, which is tangent squared is secant squared of x minus 1. And this is going to be cubed. And so all those are gone. And now I've just got secants in my integral. So now we can do the Udu substitution. We take u to be the secant of x. And du then is sitting out there for me, secant x tangent of x dx. So this time we're integrating u to the fifth times u squared minus 1 cubed times du. So it's not so great this time. I've got to take u squared minus 1 and cube it. So let me see how to do that. 1, 1, 1, oops. 1, 2, 1, 1, 3, 3, 1. It's this row here. I'm going to cube it. So we get 1 times the first term cubed. So 1 times u squared cubed. What is u squared cubed?
U to the 6.
I'm going to get a u to the 6th here. The next one is going to be 3 times u squared squared. So 1 times u squared cubed plus 3 u squared squared times 1.
Would it be minus?
It would be minus. That would be minus 1 plus 3 u squared to the first times minus 1 squared plus 1 times minus 1, or minus 1 to the 1. Or minus 1 to the third, sorry. 1, 2, 3 is the power on the minus 1. Squared first. 0 is how they go here. So there's my u to the 6th plus 3 u to the 4th times minus 1. So it gives me minus 3 u to the 4th. That's going to be plus 3 u squared minus 1. I hope I did that right.
Me too.
That's what I got, so I think that's right.
Then you multiply through by the u to the 5th and you integrate term by term. So I'm going to multiply through by u to the 5th, then get u to the 11th minus 3u to the 9th plus 3u to the 7th minus u to the 5th du. Add 1 to the power, divide by the new power. We have u to the 12 over 12 minus 3u to the 10 over 10 plus 3u to the 8 over 8 minus u to the 6 over 6. And this time each u is the secant of x. So the answers look entirely different, but they are equivalent with some trig substitutions. So the problem arises when the power on the secant is odd and the power on tangent is even. When it's not, when the power on secant is odd and the power on tangent is even, ooh, buddy.
Give up. Grades for confidence.
I agree.
If at first you
So
don't succeed, don't
Give it
try
up.
again.
power tangent is odd and the power on the secant, power on tangent, power on tangent, wait a minute, this says power on tangent is odd, so I want power on tangent is even. Is even. And this power on the secant is odd. Then more than likely, you'll need integration by parts. More than likely.
That's nasty.
Oh, it's gonna be like 14 million steps. Actually,
With
wait,
14 million
I
steps.
have a question.
Yes.
So with the sine and cosines, it usually only takes 2 steps just because they both kind
Right.
of correspond with each other. Is that gonna be kind of the same way? Is there gonna be a certain number of steps for the secant tangent?
I don't know. I don't have enough experience to know that. But I do know they get messy fast enough that some textbooks just put in integration formulas for you, and you just use the table.
Oh.
But I'm gonna integrate secant cubed. Because that has the power on tangent is 0, power on secant is odd. Integration of secant cubed is a world famous integration by parts problem. It's known everywhere it goes as integration by parts.
Is 0 really an even number?
0 is even because it's divisible by 2. Is that what you threw at me?
Yes. Unfortunately, yes.
Keep trying.
Like Ronald Reagan.
You
So
missed.
let's integrate secant cubed of x. And I want to show you first why none of the strategies over there work. Well, duh, this strategy doesn't work because I don't even have a tangent to pull out. So if I try pulling out a secant squared, if that's going to be du, then this has to be written in terms of tangent. But I don't have a substitution for secant, I have a substitution for secant squared. So shot both of those to heck. So why do I think I can do this by integration by parts? You see any piece in here that I know how to integrate rather handily? Secant squared. Let's call that dv. And then call the secant over there u. So we're going to try integration by parts. Where my u is this term. And my dv is the secant squared of x. What was the integral of secant squared? Tangent. So v is going to be the tangent of x. Here du is secant x, tangent of x dx. And integration by parts goes u v minus the integral of v du. In our example, u times v is secant of x times the tangent of x. V times du, if I kind of multiply and simplify as I do it, will give me a secant of x times a tangent squared of x dx.
We can do that.
See the v du? Secant of x times the tangent squared of x dx.
You run into the same problem again with. where you
Yeah,
have an
look,
odd
the tangent
secant.
on power is even and the tangent on secant is odd.
So we're just gonna have to get it back to secant cubed.
We're gonna get back to secant cubed, how?
Oh, and then you solve it.
And then you do the algebra.
Let's replace tangent squared with secant squared minus 1. This is gonna be one of those circular integration by parts where we're gonna solve for secant cubed. So we had this as our subsequent integration by parts integral. That's problem, so we gotta go back to trig. You can't complete the integral, you need a substitution. There it is. Replace tangent squared with secant squared minus 1.
Is there a guy who figured this out? Like, should we give him credit for this? big break?
Somebody figured it out for all secant powers. Wasn't me, I was too busy partying and having a good time. All right, tangent squared is secant squared x minus 1. Man, we're fixing the restroom upstairs. I'm so excited. We get a new restroom in this building.
Terrifying noise.
I've got like a rat or something in the wall in my office.
Got a
I
what?
keep thinking it's in my garbage can, and I'm sitting there grading papers and stuff. I hear. I'm looking at my garbage can to see if it's a rat, and it's in the wall. It could be a possum, right? Doesn't have to be a rat.
That'd be spicy.
There was-
Spicy? He's thinking of food.
Yeah, there was an armadillo. I live like out by Wolford. We had like 2 armadillos in our driveway.
That's very unusual to get armadillos way up here.
I
Yeah,
know.
we had a few possums under our shed.
We have possums because I feed some cats outside, so the
Ah.
possums think they're cats.
Also had a porcupine.
Ooh,
I had copperheads in my garage.
that ain't good.
There's a fox house like down the street. It was in my basement, you
I
know.
saw a
All
box.
right, take a look at what we get here when I distribute the secant. I'm gonna get an integral of secant cubed of x minus a secant of x. Secant cubed is what we started with. We
can
have
take
a
that out.
formula for this, if anybody remembers it.
You move it to the other side. Great.
I'm gonna move that to the other side. This one, we have a logarithm something.
Oh, natural log of secant.
All right, so I'm gonna split that up as an integral on its own.
That's right.
So this one we know. This one is the same as the one that's over here, here, here. That one's over there. So I'm gonna add it to the other side. Add to the original integral. Okay, so when I add it to this one, I'm gonna get 2 of them. So I have 2 times the integral of secant cubed of x. Then I have equals secant of x tangent of x from our first iteration of integration by parts. And then we have a formula for the integral of the secant. It's the natural log of the absolute value of the secant of x plus the tangent of x. Checking the plus c after I divide, right? We get the circular integration by parts. So I got 2 of them over here. We're going to divide by 2 and then we're done.
You add the c to the entire thing, or you add c to the top?
Doesn't matter. C divided by 2 is another c.
Figure that out.
Okay? So when you've got that combination, more than likely, you're going to get an integration by parts problem, and more than likely, it's on a secant. Because our substitution involves, if you integrate secant to the fifth, that's going to be a circular integration by parts. Secant to the seventh is a circular integration by parts, and it gets kind of painful after a while. So your book has this formula if you get a big power that you don't want to do all this. But I think everybody should integrate secant cubed at least once in their life. And if I had $1 for each time I integrated secant cubed in my life, I'd
got
probably
$2.
have like $8 or $9. That's a six-pack.
That's one way to think about it. I can remember all these. I can't remember like.
You've got to remember all this.
I don't know, it's just, I
You
don't,
remember by doing.
just like practice, like what's your trick?
You do it in your homework.
I need to make
Minus?
You write down everything you know, and then you try to work backwards.
Here's what I know,
Is it,
the integral of sine and the integral of cosine.
You slip in your book.
is it
on
minus
that.
secant x?
Slow down.
Is it minus? No, it will be plus. I blew a sign again.
That'll work too.
I blew a sign.
Let's not be this time.
That's 2 mistakes I made today. I always had this professor that said if he makes 3 mistakes in class, that's the end of class.
Uh-oh.
Wait, what did you say?
That's not one of her rules. I don't know why we're all.
That's not one of my rules,
Oh.
because that's a stupid rule.
Did he,
That would be a mistake to make that rule.
oh,
mistakes.
how many times did you get out of class though?
Never.
Never.
This professor was sharper than me.
What did you teach? Was it math?
Calc.
Yeah.
English or something?
I don't remember any classes in my life.
Just know I didn't make a mistake. That's actually right. It's just a different
Okay.
interpretation.
Let's now talk about what would happen if we're integrating cosecants with cotangents.
Oh, here we go.
It
Negative.
mimics this.
Negative, just negative.
Some of them are integration by parts. Because let's write down all of our choices for our UDUs. Let's see what I can erase. So it mimics this. So we're going to have trouble when cotangent power is even and the power on cosecant is odd. Easy ones are not those, right? So when we talk about integrating a cosecant of x to the m power times a cotangent of x to the n power. So let's work backwards. If we take u to be a cotangent, what's its derivative? Stumped you. Negative cosecant squared. What if we choose u to be cosecant? Negative cosecant of x, cotangent of x dx. Then let's derive the Pythagorean identity from this one. A cotangent is a cosine over a sine. So if I divide everything by sine squared, I have 1 plus the cotangent squared of x is 1 over sine squared, which is a cosecant squared of x. So 1 plus cotangent squared of x is cosecant squared of x, and cotangent squared of x is cosecant squared minus 1. So if we pull out a cosecant squared, I've got to write the rest of the integral in terms of cotangent. So I've got to have an even power on the cosecant in order to use this one. So this one needs an even power on cosecant. If I pull out a cosecant cotangent, then I've got to write the rest of the integral in terms of cosecants. So if I'm pulling out one of the cotangents, the other cotangents have to be even, which means I've got to have an odd power on cotangent to start with. So this one needs an odd power on cotangent. And when they're screwed up, when the power on cosecant is odd and the power on cotangent is even, you've got an integration by parts problem.
So is this almost exactly like what we just did? Just
It
with some
is
negative
exactly
signs?
like what we just did. Cotangents behave like tangents, cosecants behave like secants.
Just an extra negative sign in there.
Just an extra negative sign, exactly right. So it's a duplication of what we just had. Get them mixed up, you got integration by parts, but if they fit that right there, we're all good.
Cosecant is 6, cotangent is 7.
Let's just keep it small this time. Can you do that one real quick? Got an even power on cosecant. We'll take U to be cotangent. You don't even have to substitute anywhere. U is cotangent. I've got the du sitting for me right there.
Not that easy, no way.
Not that easy, no way? It is that easy. That's easy. U is cotangent. Du is cosecant squared with a negative sign. That wasn't a mistake. I put it right there. So we're integrating minus u squared du. Minus u cubed over 3 plus c is a minus cotangent cubed of x over 3 plus c. Agreed? It was that easy. The other case was the power on cotangent is odd. So how about we just put a 3 up there and integrate cosecant squared against cotangent cubed?
So this one would pull out
Integrate cosecant squared of x times the cotangent cubed of x. What do you want to pull out?
cosecant cotangent.
Pull out cosecant cotangent. Put a cosecant of x, cotangent of x, set up for my du term. That leaves me one of the cosecants here and 2 cotangents there. But if that's my du, everything to the left of that has to be cosecants. So I needed this even power to use the Pythagorean identity to get the cotangent out of there. Cotangent squared is cosecant squared minus 1. So if this is here, that's my du. Everything has to be in cosecants. So sub this out. What did I say that was? Cosecant squared minus 1. Now we just do the Udu substitution and finish her off. U is cosecant. Du is cosecant cotangent with a minus. So I put the minus over here with the du. And so our integral becomes minus u times u squared minus 1 times du. Well, I can multiply this out and get u cubed minus u. And if I want, I can go ahead and stick that minus in there and write it as u minus u cubed and then integrate it. And so we get u squared over 2 minus u to the 4th over 4 plus c, and each u is cosecant of x.
Shouldn't
And
the,
then u squared minus 1 should be squared, shouldn't it?
shouldn't the third be on the other u? Oh, wait, no, I
And
missed
it's
the
here
minus.
with the minus sign. So there's the u cubed with the minus, and there's a u with a plus. And then u squared over 2 minus u the fourth over 4. And now substitute back out. And so the mixed up case is some integration by parts, and just hope you don't encounter that. You would write it as a cosecant cubed, right? Integrate cosecant cubed just the way we did secant cubed. Only difference is you get a minus sign in there. We need to know how to do trig integrals because we're going to take integrals that have pesky radical signs in them and get rid of them using a trig substitution. So that's the second part of this section. First part was trig integrals. Second part, using trig substitution to simplify integrands. So part 2 of section 7.3. I'm going to use trig substitutions to help us get rid of pesky radical signs. Radical signs are pesky if they're not ordinary UDU integrals. And they're not already our inverse trig functions. Right? They're only the ones that are pesky, not the ones that we know already. So let me remind you of the ones we know already.
Is pesky a formal mathematical?
That's a mathematical term named after Bernard Pesky, famous mathematician of the 17th century.
Oh, okay.
Right.
Fact. Okay, here's what you know. You know these integrals. Yes? How would you do that?
The
Uh,
top is the derivative of the
use
bottom.
the-
so it's
The top is the derivative of the bottom. I'd integrate that as a u to the negative 1/2 integral. You know this one. Agree? What's the second one? Arc sine. This is a UDU integral. Put some junk in front, and this is the arc sine of x. Now, stick a higher power of x on top, then it becomes pesky. X squared on top, x cubed on top, x to the 4th on top. Then I can't get rid of it with an ordinary substitution. Maybe one of those bizarro substitutions that we did on that arcsecant integral, right? All right, we know how to do, so these are the ones we know. How about this one? You know that one? There's no radical sign in it. That's an arctangent. If I put a radical sign on it, then I need its derivative up here to have a UDU integral. But if I had this integral and a square root on it, there's a pesky radical sign, right? This now becomes pesky. Because it's not quite this integral and it's not quite that one. It's some bastard child of it, right? Just language from the old days.
Truth is harsh.
But draw an X through it and give up.
Right? Same deal with the, if I swap the x squared and the 1 there. If I have this That's a UDU. If I have this, that's an arcsecant. Right? Throw away the x, or put an x squared, or throw that x away, boom, there's pesky. Okay, so if it's not quite one of those, we want to try a trig substitution that's related to this. Sine squared plus cosine squared is 1. Key to life. Sine squared plus cosine squared is 1. Right? So for this thing, a squared minus x squared, it doesn't have to be an x, it could be a u. If you encounter something like that in your peskiness, like that one, but with an x squared up here or something, a pesky version of these two, then I'm going to use the fact that sine squared plus cosine squared is 1. So 1 minus sine squared is cosine squared. If I have that, I'm going to let x be a times the sine. Now I need another variable. So we pick a dummy variable. I'm not going to do a u. I'm going to use a theta. And if you substitute out an x, you also have to substitute out the dx. So dx is going to be a cosine theta d theta. Now I want you to think what this is going to look like if I put an a sine of theta here and square it.
A squared times sine theta, sine squared theta.
And that a squared is a common factor. So I'm going to factor out an a squared and what's left.
1 minus sine squared.
And what is 1 minus sine squared?
Cosine squared
So
theta.
I can eventually simplify the radical underneath the a squared times cosine squared. It's a product now. I can take the square root of each term in the product. And I've got rid of the pesky radical sign. Okay? So we do that and use the fact that 1 minus sine squared of theta is going to give us a cosine squared of theta. Radical sign is gone. We now have an integral that is a trig integral and we know how to do it. Either even power strategy or odd power strategy depends on the rest of the integrand. Okay, let's think of the other versions of the sine squared plus cosine squared is 1. Let's see, tangent squared plus 1. Oops, I want divide by cosine squared to get tan squared plus 1. So tangent squared plus 1. Let me go up here. Let me write up higher. I know that tangent squared plus 1 is secant squared from that. Tangent squared of theta plus 1 is secant squared of theta. So if I have some version of this, if I've got the variable squared added, I'm going to replace the variable with some tangent dilly. And I want to make sure I have a common factor with whatever's here. So for something that has a squared plus x squared, and this one can be in any order because addition is commutative, then I'm going to substitute x out to be a times the tangent of theta. Then we also need a dx. Dx is a times secant squared of theta d theta. So let's talk through what this will look like when we make that substitution. I'm replacing this x with a tangent of theta. So it becomes a squared tangent squared theta. There's that common factor of a squared. I factored out. What's left?
1 plus tan theta.
1 plus tangent squared of theta. 1 plus tangent squared of theta becomes secant squared of theta. I no longer have a sum. I have a product, square root of product, boom, radical's gone. Okay, the other case is the secant substitution. If I take that and write it as secant squared minus 1 is tangent squared. That tells me that if I have my variable squared in front of the minus sign, if my variable squared is in front of the minus sign, I'm going to make my variable have something to do with the secant. So I want the common factor of a, so we'll let x be a secant of theta. Then the dx is needed. Dx is a secant theta tan theta d theta. And the way we get rid of the radical sign is if x is replaced by a secant theta, you've got a squared, secant squared right here. Pull out the common factor of a squared, and you're left with the other factor of secant squared minus 1. But secant squared minus 1 is tan squared. The sum is gone, product's there, radical's gone. Those are the only 3 cases. If there's a plus sign between the 2 terms, that's a tangent substitution. If the minus sign is in front of the variable, it's a sign substitution. If the minus sign is behind the variable, it's a secant substitution. It's all because of this. So what are we going to do? I'm going to do this integral. Where can I go? I've got about the x squared up here and a 4 minus x squared here. That radical sign doesn't have to be in the denominator. It could have been in the numerator. In the numerator, it would still be pesky because it wouldn't be a UDU. So which case do I have here? It's a sign because the variable squared is behind the minus sign. You've got to always check. If it were x to the first power, don't do that trig substitution. It takes too long. If that were gone and I have an inverse sign, done, right? It's only when it's pesky that you need to go to this extreme measure. These take quite a while, but they're rinky-dinky steps. So take a deep breath. You good?
So what work on this due tonight, right?
It's doing about 2 hours. Okay, so I've got the minus sign. I'm going to take x. What am I using as my a?
2.
2. Because I want to square the 2 and have a common factor.
So, all right, so for this, we're taking a sine theta, right?
Correct.
Our sine, so could we like in a definite situation, or is this just for non-definite intervals?
You mean if I had numbers here?
Yeah, so like,
Yeah, you can use it in any interval you want.
would that theta have to be given? Or would you?
No, I'm going to show you how to get us back to x.
Okay.
We're going to get a simple integral in terms of theta, but then just like when we do a UDU, we get everything back to x. We're going to get back to x as well. Okay. All right, x is 2 sine theta. Don't forget the dx. That's where students typically make their mistake. Dx doesn't magically turn into d theta. Dx in this case turns into 2 cosine theta d theta.
Oh, wait, I can see why this gets problematic.
Each x is 2 sine theta. Dx is 2 cosine theta d theta. Let's see what our new integral looks like. So I'm going to have an x squared. So that's going to be 4 sine squared theta. Downstairs under the radical sign, I'm going to have 4 minus 4 sine squared theta. And then the dx becomes 2 cosine theta d theta. The point of this was to get rid of the radical sign. So let's work underneath the radical sign. So note that 4 minus 4 sine squared theta becomes 4 times 1 minus. This is the part we did in our head a minute ago. And 1 minus sine squared is cosine squared. So just looking at that, we have this. Now I'm going to put it back in. I've got 4 sine squared theta here. I got 2 cosine theta here. And the d theta. My radical becomes 4 cosine squared. Is that too much?
Who's gonna end up canceling it?
It's going to cancel out. You okay? Follow all that? So that denominator is just a 2 cosine theta. I'll put it in.
So are we gonna have to solve the data like we're trying to solve for you?
Yep,
Okay.
But you have to like make it arc sine, right?
won't even be that hard. We use right triangle trigonometry. Cancel there, and we're integrating 4 sine squared of theta. Remember the integral of sine squared of theta?
It's theta over 2 minus sine of 2 theta over 4.
Use the 4 from the front. Theta over 2 minus the sine of 2 theta over 4.
Like the one thing I've memorized.
Well, now I'm going to change the game a little bit. I'm going to use a double angle formula here. Who remembers the double angle formula for the sine of 2 theta?
2 sine
sine
theta.
theta.
2 sine theta cosine theta.
Yeah, I was wrong.
Okay. Now we got to get back. The reason I wanted to do that is, look, I know what the sine of theta is. What's the sine of theta in terms of x?
X over 2.
X over 2. I didn't know what the sine of 2 theta was. It's not as simple as putting a 2 in front of everything. But if I know the value of one trig function of theta, I know them all. This says that the sine of theta is x over 2. That's why I wrote it like that. I'm going to put an x over 2 here. But now let's figure out what the cosine of theta is. I can use my Pythagorean identity. Cosine squared is 1 minus sine squared. Solve it that algebraically, or I can just do it in picture form. The picture that says this is this. Here's a right triangle. Let's put angle theta here. This describes 2 sides of that right triangle. Which 2 sides?
Opposite hypotenuse.
So the opposite is going to be x, and the hypotenuse is going to be 2. I'm going to need the cosine of that angle, so I need the adjacent side. What squared plus x squared gives us 2 squared? Try it, put a letter here. I have that a squared plus x squared is 2 squared. Solve for a. Should always be the thing you started with. Then from that picture, I can get that the cosine of theta is the adjacent over the hypotenuse. And we've got everything in terms of x and we're done. Oh, almost. What do we do about that?
Arc sine.
That's right.
Okay.
If the sine of theta is x over 2, then theta itself is the arc sine of x over 2. So get in that little bitty spot there. Theta is the arc sine of x over 2. Now we can write our answer. It's 4 times the arc sine of x over 2 divided by that 2. I'm going to go ahead and cancel one of the 2's here. Sine of theta was x over 2. Cosine of theta is the square root of 4 minus x squared over 2. Then I've got a 2 here. And whatever simplifying you want to do beyond that is okay with me. Maybe just send the 4 through there.
Which work.
I don't know. I won't simplify much. But we gotta get it back to X. So that's if the minus sign is behind, I mean, the variable's behind the minus sign. That's a sign substitution. You follow all that?
Yeah, partially.
Yep.
I think I lost part of my brain though, thinking part of it repeated in notes, so.
I think-
So,
I think the last term is multiplied by 1/2 instead of 2.
I did that and I left so you're right, I can cancel one more 2 and have a half. So I can simplify way beyond that. Okay, so I want to show you next time the tangent substitution and the secant substitution. I kept you a little bit long last time, so I'll give you the 3 minutes here.
We need it for our web work this year.
You do need it for me, I'll do it in 2 hours. It's now an hour and 45 minutes that it's due. I do have some homework papers up here. I think I'm caught up with my grading, so check Blackboard. If I'm missing any of your assignments and you turned it in, let me know and I'll go hunting for it. If you're missing any assignments and you haven't turned it in, turn it in.
Feeling good?
Any graded papers are.
Oh, yeah.
One that I remember. Fantastic. Sorry.
Yeah, I mean, I have.
I got it.
The first couple of questions done.